So with this fourth sphere or the fourth satellite, we are going to be able to find your exact location. Does that make sense? Did everyone understand it?
So it's
Sorry?
the function of satellite.
Yeah.
The kind of finding the pieces.
Well, all the satellites together, the function is find your precise location, because it's, if you remove any of them, either satellite A or B or C or D, you're not going to be able to get your precise location. So it's not specifically about which satellite, but how many you have.
Sorry, Professor. Could you please repeat the working of the fourth satellite, how it helps with the altitude?
Yeah, so wait. So on the third satellite, remember from the 2D explanation that I gave you, in the 2D, you have only horizontal plane, right? So where you intersect between the three circles, it's going to be your location, because there is no altitude, it's just a plane. But when we are talking about 3D, let's say you intersect those three satellites, you know the location, but let's, think about your vertically. You know your location is here in this, on this 2D plane, but you don't know if it's in this location here, 2 feet above or 1 feet below, or, 10 feet above. So this is the why you need the fourth satellite, is to narrow down to the exact location horizontally, so in the surface, but also know, the height. You can be in a location that it's, 1 feet tall, or you can be in a location, let's say that you're on the top of a mountain, it's going to be a couple hundred or more than 1,000 miles, not miles, but feet tall. So the fourth satellite is going to add the information of where you are vertically, like in the Z plane. So it's going to be like your 3-dimension. Does that make sense?
Yes, thank you.
Yeah, so when you add this fourth satellite, you can narrow down your location with an accuracy between 5 and 10 meters, which is still, it's good, but not so good for many of our purposes in precision ag. But the more satellites, 4 is the minimum you can have, but it doesn't mean that every time you have your receiver, you're only going to be capturing 4 signals. Most likely, you're going to be capturing at least 7 or 8, sometimes more than 10, 12, 14. So every new satellite that signal that you're able to that your GPS receiver is able to capture, you're going to slightly increase your accuracy, because you're going to narrow down more every time you add a new satellite. So with more satellites, you can narrow down your location with an accuracy of 1 to 2 meters, which is pretty good. 1 to 2 meters, you can use that in many applications of precision ag.
Like in space, how these satellites know its position with this same principle, or it's always fixed?
So
because satellites send his position to us.
yeah, so the way you're gonna know is because when the satellite sends a broadcast a signal, it has a lot more information than just the speed or the time. It has the ID of the satellite, it has the location in the orbit. So it has a lot more information that tells you, your receiver, which satellite you're receiving that signal from and where that satellite is.
No, like how, because we know place through GPS, that where that place is. So how satellites or the satellites talk to each other, that yeah, with the same principle, that where all 4 satellites.
That's an interesting question. I don't think satellites talk, because the way, so what determines where or how the satellite's going to function, it's the messages that it's sent from the master stations.
Oh,
So that's why we have the control segment.
throughout.
Yeah, so it's collecting data continuously. So let's say that a satellite goes off orbit. I don't know if that's ever happened, but let's say that it happened. So the control stations are going to be capturing data, and if it senses there's something wrong, the master control stations are going to send data to correct positioning of that satellite. So that's how the satellite know where they are. But I don't know specifically if one satellite knows about the other one. But this control comes from the control segments from the master stations. Sorry. So we've talked about already on how the GPS receiver calculates the distance from the satellites. We also know that the radio waves or the radio signals, they travel at the speed of light, and this is going to be 300 million meters per second or 186,000 miles per second. So the receiver, again, is going to calculate how far the signal has traveled. So, the time from when it was broadcasted to the time you received that signal by timing this difference. However, I mentioned to you in the beginning of the class that satellites have atomic clocks, which are very, very accurate, but your GPS receiver does not have an atomic clock. So if you need to know when the time the satellite broadcasted the signal, and that time is gonna be very accurate because it's based on an atomic clock. And you need to know when your GPS receiver received that signal, and that timing is not going to be so accurate, right? Because your GPS receiver does not have an atomic clock. So because of that, we have to synchronize our GPS receiver clocks with the satellite atomic clock, so we can mitigate the errors that can be, added to your position calculation because of errors in your GPS receiver clock. So to measure travel time, again, GPS receiver must know when the signal left the satellite. And to do this, the clocks on the receiver are going to be synchronized with the atomic clocks on the satellite. So every time a GPS receiver receives signals from satellites, it adjusts its own clock based on the information that we received from each satellite. So your GPS receiver is continuously changing or adapting its time based on atomic clocks. So with that, we mitigate this error of not having such accurate clocks on our GPS receivers. And you might think, okay, how often does that happen? So satellite sends signals, I don't remember how many times now, but it's multiple times per second. So this is happening continuously. And again, your GPS receiver, when you have it out with you, depending on your location, you're going to be capturing signal from multiple satellites at a time, more than 10, most likely. So you're receiving multiple signals with information from multiple satellites, multiple times per second. So it does a pretty good job at, trying to mitigate this error because of your the poor accuracy on your clock that you have on your GPS receiver. But your GPS receiver also needs another very important piece of information. And well, it's already on the screen, but can someone tell me what other kind of information you need? For me to calculate my distance from you, for example, what other information do I need to know?
Distance, time.
No, I need to know where you are. Because if I don't know where you are, I'm not going to be able to calculate my distance from you.
Yeah.
So we also need what we call almanac of satellites. And the almanac of satellites are going to show you all the location information about every satellite in the sky. And you can download apps on your phone that shows you the almanac of satellites. So, for example, this app here, the GPS data, I know that they have this app for Android, probably for iOS as well, so everyone can download it. And it's gonna give you your location here in longitude, latitude. It's gonna give you a lot of other information. For example, here, how many satellites was I seeing at that time? As you can see here, it's a lot more than 4, right? 19 satellites were used to calculate my position. And it gives you a lot more information here. But in the second screen here, what is interesting is that it shows you the almanac of satellites. So it's going to show you the location on the sky that each satellite is located at that time that you're trying to see your location. So of course, the reference is gonna be you. So here, just an example of a couple satellites that were on the sky. So you can just use this app on your phone at any time, and you can see which satellites your phone is receiving data from and where the satellites are on the sky. Yes.
So basically, at starting you said that it's univariate, like a signal that satellite only send signal
Yes.
to receiver. But then how it knows position of me until I don't send my location back?
You don't send your location back. You
So-
calculate your phone knows, the satellite doesn't know where you are, you know. So
Oh, yeah.
you have your GPS receiver
So yeah,
here, right?
that's helpful.
So it knows, because again, when the satellite sends signal, it sends a lot of information. It sends the ID of the satellite, it sends the location, the orbit, it sends the timestamp of when the signal was broadcasted. So because of that, it's very easy for any GPS receiver to know where the satellites are. And then based on your location that your GPS receiver calculates, the app can show you where the satellites are based on you, because the app knows where you are. Does that make sense?
So, does it mean like the satellite does not calculate anything, every calculation is done on the signal?
For your specific position, yes, but for sure they have thousands of equations happening there to make sure that the system is working. But to calculate your location, the satellite only sends the signal, and your receiver is going to calculate that for you. So, and then on the third page of this app, you have here your location. So this acts like a Google Maps. It shows you where you are. But it's just interesting because, you know, it shows you more information than common apps we use for navigation. So GPS receivers, and when I say GPS receivers, what I mean is, you know, any equipment that has a GPS chip. The GPS chip is what is going to make an equipment be able to calculate your location and to use navigation and everything else. So there are many kinds of GPS chips. Of course, they're going to be ranging in price. And it's pretty amazing on how small, you know, we've been able to achieve with new GPS chips. We have, you know, some chips that you can purchase online by a couple dollars, maybe cents, if you buy it in bulk. Of course, based on the price, you're going to have, you know, a variety of accuracies. Very cheap GPS chips are going to give you maybe lower accuracy for precision ag purposes, but still, it's a pretty amazing technology to have for such a low price. So I talked about in a couple slides back of some errors that can be added to the calculation of your position, right? So now I'm going to list to you which are those errors and then explain each one separately. So when you're calculating your location, you know, like I said, you can calculate it pretty accurately, but, you know, it's going to depend on your perspective. For some people, like when you're using Google Maps, you don't need your location to have an accuracy of, you know, 2 centimeters. if it has an accuracy of a couple meters, it's fine for that use. But for other purposes in precision ag, for example, if you're using an auto steer system to plant, and you want that to be precise every year, then you're gonna need a centimeter accuracy. So your machine knows that, you know, within a centimeter or two, where you should start your row each year. So it depends on your purpose. You're gonna have different perspectives of what a good accuracy is. But we are never able to calculate our location 100% accurate. And there are some reasons for that, and many of those is because of these errors that are added to the whole system, and we're gonna go through each one of them. So the first one is because of the ionosphere and troposphere induced delays of the radio signal. So the next slide, I'm gonna go in depth on that, but basically, you know, when the satellite broadcasts a radio signal, it has to go through all the atmosphere until it reaches you in the surface of the Earth, right? There are things on the atmosphere that can delay that signal. So if you're calculating your location, remember the equation. To calculate the distance, you need to know when the signal left and when it arrived. But if the signal, and you know that based on the speed, you know the exact speed. But if something along the way makes your signal slower, then you're gonna add a small error to your calculation. The second error that can be added is from your GPS receiver clock. I already talked about that. We try to, the GPS receivers clocks are synchronized with atomic clocks to try to mitigate that error. The third error is gonna be the signal multipath, and I'm gonna talk about that in a next slide. Then we have orbital errors, because satellites, they are supposed to be in a specific orbit, but they deviate from that orbit sometimes because of gravitational pull from Earth, Moon, etc. And we also have the DOP, which is dilution of precision. And dilution of precision is an important indicator when you're using GPS receivers, because it's gonna tell you basically the strength of your current satellite geometry. That might not make sense to you, a lot of sense to you right now, but I'm also gonna explain that in depth. So we have atmosphere delays to GPS, to the radio signals. We have errors because of a GPS receiver clock. We have signal multipath, orbital errors, and dilution of precision. So let's go through each one of them. My phone, so I can keep an eye on the time. The class goes until 11:10, right? Yeah. So the first error is gonna be added by the ionosphere and troposphere. So in this image here, I just want to show you, if you don't remember that, but Earth's atmosphere has 5 different layers. So closest to the surface, we have troposphere, then we have stratosphere, mesosphere, thermosphere, which is also called ionosphere, and then we have the exosphere, where our satellites are located. So when the signal propagates through these different layers, in those 2 specific layers, the ionosphere, which is the second from the top, and the troposphere, we have some factors that delays the signals, which is for the ionosphere here on the top, the second from the top, we have a lot of charged particles that can interact with your radio signal and delay the signal when it's passing through that specific layer. We also have here on the troposphere some factors related to water vapor particles that can also delay your signal. And I'm not saying this happens in every one of those layers, but compared to those 2, the errors are very minimal. So that's why we speak about these 2 layers, because they're the most important to, you know, related to this error. They are the layers that are gonna add the most delay to your signal. So Did everyone understand this? Is that okay? No?
I see like, those spheres, I didn't like know which one is interfering much, like those areas.
So this one, thermosphere, is the same name as ionosphere. They're the same one. It's just that it has two names. So this one, the signal is delayed because of electrons or order particles that have charge. And the other one is the troposphere, which is the one closest to the Earth because of different water vapor particles. Like I said, the other ones also adds error, but it's minimal compared to the ionosphere, which is the thermosphere, and the troposphere. So the second type of error comes from the signal multipath. So again, going back to the equation, the way we calculate our position is calculating distance, right? The distance is going to be based on the speed of travel of that signal and based on the time it took from that for that signal to leave the source, which is the satellite, to your GPS receiver. However, sometimes these signals, they don't go directly from your satellite to your receiver. Sometimes if you're near big objects, this signal is going to bounce on another object and then be reflected to your GPS receiver. So if your signal bounces from another object and goes to your receiver, this is going to add to the time of travel, right? Because it's going to take more time. It's a bigger distance. So this is going to add an error because that added distance to your signal path is not related to the distance to the satellite, but it's related to just the signal being reflected. So this is going to affect the calculation of time that the signal took from your satellite to your receiver, because the signal bounced somewhere else before it reached your receiver. So this is going to cause an error. And this is a very unpredictable error. For example, the last error that we talked about, the atmosphere effects, it's more predictable. We can have equations and try to predict how much, the atmosphere is going to slow down the signal. So it's easier to mitigate that error because it's predictable, but you cannot predict if the signal is going to reflect from somewhere else. So this is a very difficult error to try to solve, basically. Wait, did I skip? Oh. Wait, I thought I had another slide. So let me go back and talk about the dilution of precision. Well, the orbital errors, there's not much to explain there. Satellite is supposed to be in an orbit. Sometimes it deviates a little bit because of gravitational pull. So this adds an error as well. But the fourth or fifth error, which is dilution of precision, what does that mean? So when I mentioned this previously, I said that the dilution of precision is going to be related to the strength of your satellite geometry. So let's take a look on this image here to understand what is the satellite geometry. So let's say that I'm, in a field here in Georgia, it's, open field, and many of our fields here, we have a lot of wooded area around fields, right? So let's say that I'm in the middle of this field with my GPS receiver, and I'm right next to this wooded area. Am I going to be able, or my GPS receiver going to be able to capture signal of satellites there west of me?
On the side of woods.
On the side of the woods? No, it's not going to be able, right? Because the woods, trees are objects that affect the signal of satellites. So you're not going to be able to capture signals from that side. So probably all the satellites that you're receiving signal from are going to be grouped on the other side, on your east side, which is the first case here. So this makes the dilution of precision increase. So you have a bad geometry because this is going to give you a biased calculation of location, right? Because all your reference is only grouped in one side. So this is not good. And your GPS receiver is going to show you, you can look at that information, the DOP. So before you press to actually collect your GPS, your coordinates, if your DOP is high, we usually try to move around if we can, try to find a better location in which the signal is not being blocked by anything, so we can capture satellites that are distributed in a better geometry and not only grouped in one side. So if you're in an open field and your GPS receiver can see satellites from all around you, then it's going to give you a low dilution of precision, which is going to be a good geometry. So this is going to be more accurate because you have a better distributed geometry of the satellites. So this is, the dilution of precision error. And this is very common to happen, actually. So when I was an undergrad, I worked in a company that did surveys and mapping. So I used to go to farms to collect and map the boundaries of the farms. And in Brazil, in my region, we have a lot of mountains and woods, very dense woods as well. So sometimes we would stay 10, 20 minutes trying to get signal because we were in the middle of the woods. Sometimes we have to try to chop some trees and see if a signal could get through. So this happens more than you think. And here in Georgia as well, we have this problem that many of our crop fields, they are surrounded by pine trees and things like that. So this can happen as well if you are on the corner of the field.
Like how we know that it's high DOP or low DOP, because on Trimble is only tells that how many satellites are there.
No, it does show you. There are some
old article. I think then I use the old article in that it's just show number of satellites.
So now I don't remember if cheaper GPS receivers, but I think all of them have them. I know that better GPS receivers, the ones that I was using for my purpose of surveying, we needed very high accuracy. So they did show a lot of the information. So you could see in real time your DOP value. And I do believe all GPS receivers, I don't think your phone is going to show it, but a GPS receiver is going to show it.
What's a good or bad DOP value?
Oh, that's a good question. I can check for you. I don't remember right now. I believe around the DOP, it's it's not a high number. I think it's around 1 or 2, but I can check that for you.
And what makes one GPS receiver better than the other?
Calculations and frequencies that they can receive. So some GPS receivers, they use newer equations than older ones, and some GPS receivers have the ability to capture signal in different frequencies than others. That's of course, I think there are more reasons, but that I can remember right now is these two. Because, for example, even when if you purchase a GPS receiver, one of those common ones used for agriculture, for example, I believe some of them can only capture L1 and L2. And when we talk about L1, L2, L5, these are just different frequencies. I think L1 is around 1500 megahertz, and then L2 is around 1300, and then L5 is 1100 megahertz. So it's just different frequencies. So some of these GPS receivers, they can only see L1, or they can see L1 or 2, and better, more expensive receivers, they're going to be able to see more frequencies. So they're going to receive more data. And well, you would think that why not just do that for every receiver to be able to see all of that? But it's just when we talk about, for example, new cars, they have the capability, but if you don't pay, they don't activate that on your car to be able to do something. It's just, if you have all the receivers using all the best equations and seeing all the frequencies, then they cannot charge you a higher price. So, okay, we still have time. There are some ways that we can try to mitigate and correct for these errors. And one of the ways is a technique that we call DGPS, which is differentially corrected GPS. And this, basically this technique, the basis for the technique is we're gonna use a known location to calculate and correct the error of our receiver, which is in an unknown location. So let me give you an example so it's easier to understand. So here we have an example of a base station and a mobile receiver. The mobile receiver is the GPS that you carry around. Base stations are stations, they're created and they're spread around the whole country, and in every country we have different base stations, multiple thousands, I don't know, it's a very high number of stations that they are fixed in a location with an antenna to be able to calculate a GPS error and then send that equation, that calculation to your receiver so you can calculate and correct for the error or in your own location. So here we have a base station, and this is the actual position of the base station. Every base station that is registered, we know the exact location. And then we have, you know, let's ourselves with a mobile receiver, and we have our actual position, but we don't know, right? I don't know my actual position right now, down to the, you know, centimeter. That's why I'm using my GPS receiver. We are both trying to collect our position at the same time here. So the base station is also going to be seeing the satellites, right? Your receiver is going to be seeing probably the same or similar satellites, because to do this type of correction, you use signal from base stations that are near you. So there are stations, for example, spread all around Georgia. And if you go to Macon, Georgia, to Tifton, to Athens, you're probably going to have stations, different stations close to you. They're going to be used to do that correction. So the base station here knows its own position, the accurate position. And at the same time that you are trying to find your position, this base station is always using the same signals, the same information from the satellites to calculate their position. So the base station is gonna use an equation to calculate what is the error that it's giving from the calculated position to their known position. So with that, we're gonna be able to know what is gonna be the exact error that is probably gonna be happening when you calculate your position. So here we have your actual position that you don't know, but your GPS is showing that your calculated position is here. Remember that I told you that GPS gives you an accuracy of 5 to 10 meters, or depending how many satellites you see, can go down to 1 to 2 meters. So you're gonna be off from your actual position. But then the base station calculates this error and then transmits a message to your receiver with that equation. So the receiver can apply that equation to your calculation. And from that initial calculated location, now after applying that equation, you're gonna have a differentially corrected position that is much closer to what your actual position is. Does everyone understand that? This is an important concept to understand, because we are gonna see that there are different types of corrections. The DGPS is the correction. We're gonna talk about that, but we have available in every GPS. Your phone is using this correction right now, but we have other corrections with much higher accuracy, and we're going to talk about that. So some sources of DGPS correction. We have many sources. One of the sources, and I believe this was more common in the past when DGPS was developed, we had subscription to private providers via satellite broadcast. And this was OnStar, was a company, this other company, Fugro. And at that time, this was the most accurate signal, depending, of course, on your receiver quality. So you can get the signal, this correction broadcasted from satellites. Nowadays, we have other systems that we call, well, the American one is called the augmentation system, wide area augmentation system, that you can also get this correction from. And this one is free, and it's what you use all the time. The European Union also has a source of DGPS, or differential correction signal, which is called EGNOS, which stands for European Geostationary Navigation Overlay Service. We also have other three sources of DGPS correction, which is State Departments of Transportation beacons, which is widely used or was widely used by the Coast Guard and Marines and etc. We also have real-time kinematic, RTK, and if you work with precision ag, you hear this term all the time, RTK, and we're going to talk about that as well. And we also have the correction from cellular modem or internet. So let's talk about the first one, the DGPS with beacon correction. So this is the original public source of DGPS, so you don't need to pay for that, but was discontinued in 2020. So how does DGPS with beacon correction works? The same concept that I explained when we started talking about correction applies here. So we have satellites in the sky in our constellation, and our boat here has a GPS receiver. So at the same time that your GPS receiver on your boat is receiving signal from these satellites and calculating your position, a nearby beacon has also a GPS receiver and acts as a base station. So at the same time that you're trying to calculate your position here, the beacon is also, the base station at the beacon is also calculating its position, but we know the actual location of this base station. So it's going to calculate that error equation that I told you, and it's going to broadcast or send that correction message to the GPS receiver on your boat, and you're going to be able to correct your position. So this is called the DGPS with beacon correction, but was discontinued in 2020. We also have other types of differential correction signals. So pay attention to this one, because for some people it's difficult to understand what is the difference between each one. But so I'll do my best to try to explain this. We also have the DGPS correction with WAS, which is the augmentation system, or the EGNOS, which is the European version, or OnStar, which was the paid version that I don't think people use it anymore, and etc. So the concept here is going to be similar to the DGPS with beacon, but the difference is that, for example, here you have a GPS receiver on your tractor, and the satellite is correcting. You're receiving signal from different satellites, and then you have a base station that is also doing the same thing, calculating the equation to correct the error. But instead of transmitting this correction message directly to your receiver, it's sending through a control station to a geostationary satellite in space. And a geostationary satellite is fixed in space. It it's synchronized with the rotation of the Earth. So it's, you know, in every place you look, it seems like it's fixed. And the role of the satellite is to broadcast this correction message. So it's another satellite. So instead of sending that correction message directly to your receiver, this correction message goes to this satellite through a control station. And from the satellite, it sends to your receiver the correction message. Does that make sense?
Satellite, so we got that error. So the system send message to satellite back. And then satellite send that information to the satellite.
No, not the satellite back again. So once again, we have the satellites that sends the signals for your GPS receiver, right?
Yeah.
You have here on your tractor. The same satellites are also sending signals on your base station here. And your base station is calculating that equation to correct the error. From here, you remember with the beacon, the correction message would come directly from here to here, right? Directly from the base station to your receiver. But in this case, with WAS and the other types of companies, the signal doesn't go directly here. It goes to a geostationary satellite, and that satellite sends directly to your receiver. So the satellite doesn't communicate with the other ones.
It goes to every satellite, whichever it is.
Now,
connected.
a geostationary satellite. Not all satellites are geostationary. Yeah. So just look at the arrows here. So your message, correction message goes to here, and then it goes directly to your receiver. So we can now think of the advantage of that, right? Because if you have...
Geostationary satellite is not GPS satellite.
It is, but it's in a geostationary. Yeah. So, and in the constellation, I don't remember how many of the satellites are geostationary. I remember for the Chinese one, they had 3 geostationary, but I don't know I don't remember for GPS. So the advantage of that is when you use the GPS, the DGPS correction with a beacon, the station or the beacon had to be near you, right? But when that correction message is sent to a satellite, then it can be sent to multiple receivers much easier. So this is what we use right now. So even with aviation, you have, you know, the correction messages being sent to the GPS on an airplane to know where the airplane is using WAS or EGNOS. So these messages, correction messages, are going to be broadcast by geostationary satellites. So once again, so we fix that on our minds. With the DGPS with WAS, the correction, you know, your receiver calculates its location based on GPS satellites. The base station calculates the location and then uses the equation of correction, sends that equation of correction for the error to a geostationary satellite. Then this geostationary satellite sends it to your receiver to apply the correction. So now we have the other type of differential correction, which is RTK. And RTK requires subscription because it's high accuracy. So if it's high accuracy, then, you know, what it's free, of course, they're going to charge for you to use it. So the RTK, it's a highly precise technique, which is going to give you a 1-inch accuracy from year to year. So let's say that I have an RTK correction on my tractor, and I plant my corn row here in 2021. In 2022, I can use that same coordinate, same map in my tractor that has an auto steer system, and it's going to be able to plant that seed only 1 inch apart. That's how accurate this is. And that's why, of course, they charge it for you to have that signal, that correction signal. So with the RTK, one GPS receiver is set as the base station. So we have a base station here with an antenna with a GPS receiver. That, of course, is going to be a very good GPS receiver. It's going to be able to get information from more frequencies. So you're going to have that GPS receiver acting as the base station. And then the concept is similar with the beacon. You are going to be receiving signals from the satellites, trying to calculate your position. The base station here is going to calculate that location as well. And this base station, we know the location. These base stations are set up around the country. We already know their actual location. They are going to calculate the error equation and then send directly to the tractor. So what is the difference between RTK and the DGPS with beacon then? It's basically going to be, because the concept is the same, right? You have the base station that sends the correction message directly to your receiver. But the difference is going to be on the accuracy, because for RTK, RTK uses different and more and newer, better, more accurate equations than DGPS. And RTK also is able to capture more frequencies. So that's why the correction from RTK is more accurate. It's basically because the equations and the frequencies that are used are higher and better than DGPS, which is free. But we also have a second type of RTK, which is similar concept. The only difference is going to be that you can buy your own base station for RTK. So instead of relying on base stations that are already set up around the country, and let's say you want very, very accurate data, you can go and buy your own base station, and then you can carry your base station and put right next to your field and use that to send corrections to your receiver. But because these base stations, they're already set up around the country, we already know their location, right? So, but if we buy our own personal base station and we move it around, how do you know the actual location of that base station to calculate the error? When you have your own personal base station, you have to set it on the field for 30 minutes to have a stable signal. And then the base station, of course, is expensive if you want to buy your personal one. And the antenna has to, the base station has to stay there for 30 minutes at least to be able to get a stable signal and calculate its own location. And then it can send the message to your receiver. So again, the difference between RTK from towers and RTK from your base station is that the towers, they are already installed in different places around the country, but your personal base station, you can just carry around and put next to your field, because sometimes, and we are going to show this in the next class, the towers that are installed, these towers are from different companies, so the coverage is different. So let's say that you're somewhere very rural Georgia, and your nearest base station is like 30 miles from you. The signal is going to be weaker, so this is going to increase or decrease your accuracy a little bit. So the closer you are to your base station, better your correction is going to be, better the signal. So that's why some people, some farmers that wants to have the money and wants to make that investment, they can purchase their own base station, so they don't have to rely on base stations that are already set up, because sometimes you have a field that is far away from most base stations. So the correction you get is going to be lower accuracy than if you have your own base station. So these are the different types of DGPS. We're going to stop here today, and we can just pick it back up on Friday. But I hope this was clear. The different types of corrections. This is something you guys are going to need to know. So please, if you didn't understand, email me, we can see it and I can explain that to you again. But I want to make sure that you guys understand this concept. So I see you guys on Friday. Yes.
but not related to this.
Ah.
So like, if we can buy a base station, personal base stations,
Yes.
can our phone be used as a receiver or not?
No, because your phone doesn't have,
RTK.
it doesn't have
Perhaps, like,
capability
we
for
we
RTK.
got an RTK drone. And if I want, because I know that right now, Leo can't.
Wait a second.
Oh, yeah, I can talk later.
Is everything okay in Tifton? Yeah, if you have any questions, you can just email me and,
We're all good here, so.
okay. So I see you guys on Friday. But if you have questions, please email me. Thank you.
All right. See you. Bye bye.
I'll work there in the summer. Oh.